Hi, I will discuss joint work with Vishesh, Jain, and Thuy-Duong Vuong on an algorithmic counting and sampling version of the Lovász local lemma. We will be interested in constraint satisfaction problems, so we are given variables x1 through xn, which take values in finite domains. So for us, we'll be thinking about these xi as independent random variables, usually uniformly distributed in the finite domains. And we have a set of constraint script C that consists of m bad events. We can think of the event Ci as the event that constraint I is violated. We assume that each constraint Ci depends on a subset of variables V of Ci. And from here, we can construct the dependency graph of the instance, which is a graph on the constraints where two constraints are connected if they share a variable. And the parameter of interest is the maximum degree of the dependency graph, which we denote by delta. So this is what comes up often in the Lovász local lemma. And we'll denote by Ci bar the complement of Ci. So this is a good event. In particular, a solution to the constraint satisfaction problem is simply a point that is contained in the intersection of all of these good events Ci bar. We'll call Pi the probability of the ith bad event and P the maximum probability of a bad event. So what are some motivating examples of constraint satisfaction problems? We have KCNF formulas, which are simply a logical AND of a bunch of logical ORs of K variables. So for example, here is a 3CNF formula. So a KCNF formula is a constraint satisfaction problem where each constraint is simply this logical OR of K literals. Another example is that of hypergraph colorings. So given a K-uniform hypergraph G and a set of colors Q, a proper vertex coloring would correspond to a solution to the constraint satisfaction problem where we set up one constraint per edge, which represents the condition that the colors of the vertices V in that edge are not all identical. So the Lovász local lemma, as we stated here in one of its most basic symmetric and variable version form, says that if the maximum bad probability P is bounded by 1 over E times delta plus 1, then there exists a solution to the constraint satisfaction problem. In particular, we have a positive lower bound on the probability of the intersection of all M good events. We'll call this condition here the LLL condition. So what does this LLL imply in our two examples? In the case of KCNF formula, it implies that there will always be a satisfying assignment if delta, the maximum degree in the dependency graph, is roughly smaller than 2 to the K over E. And in fact, if we use a lopsided version of the LLL, then this condition can be improved by a factor of 2, which is also asymptotically tight. In the case of hypergraph colorings, the Lovász local lemma implies that there exists a proper coloring if we have that delta is roughly smaller than Q to the K minus 1 over E, or other words, Q is at least delta to roughly 1 over K minus 1. Okay, so the Lovász local lemma would imply that there exists one solution, but doesn't tell us that we can find a solution efficiently. So for example, in the case of a KCNF formula with delta smaller than 2 to the K over E, can we actually find a satisfying assignment efficiently? So even though we have a lower bound on the probability of satisfaction in the Lovász local lemma, naive rejection sampling would not work because in the regime of parameters that we are interested in, that is when K and delta are fixed as constants and M and N are tending to infinity, this probability lower bound is exponentially small. However, we do know through a long line of works that there are efficient algorithms for finding a satisfying assignment. And it starts from the work of Beck in 1991. And in the groundbreaking work of Moser and Tadeusz, we already essentially have an efficient algorithm for finding a satisfying assignment, essentially in the region matching the LLL condition. So that is for finding a single satisfying assignment. What if we want to approximately sample a satisfying, a uniformly at random, a satisfying assignment, or approximately count the total number of satisfying assignments? It turns out that under this LLL condition, it is actually NP hard to approximately count the number of satisfying assignments. So in the work of Bezakova et al., even for delta equals to 2 to the K over 2, and even if we restrict to monotone instances of the KCNF formula, that is, we don't have any variables with a negation, it is still NP hard to approximately count. And let's note that in the case of monotone instances, if we want to find one satisfying assignment, it is actually trivial because we can simply set all of the variables to true. So now let's move the threshold from 2 to the k to 2 to the k over 2. Can we now approximately count efficiently? It turns out that in the case of monotone formula, the answer is indeed yes, and this is given by a work of Pham, Lai, and Jain. And in other works of Guo, Jerome, and Liu, approximate counting and sampling algorithms are also provided, assuming certain structural properties of the KCNF formula. For example, if they are extremal, or if two constraints are either disjoint or will overlap in many variables. Okay, what about general KCNF formulas with no additional assumption on a structure? In this case, Moitra provides a deterministic algorithm that approximately count the number of satisfying assignments as long as delta is smaller than 2 to the k over 60. So it's off from the LLL condition by this factor 60. And the running time of Moitra's algorithm is big O of n to the poly of delta. So this is only polynomial time if k and delta are fixed as constants. However, let's note that typically in the works that establish deterministic approximate counting algorithm, this type of running time is what we typically see. In the setting of randomized algorithm for approximate counting and sampling, this constant 60 in Moitra's work is improved to 20 and then 13. And also the running time of this randomized algorithm is much smaller, so it's nearly linear in n. In another work of ours last year, we improved the constant 13 to 5.71, and this was also obtained subsequently in a work of He, Sun, and Wu. Let's now turn to the case of proper Q colorings of K-uniform hypergraphs. In this case, LLL guarantees the existence of a coloring provided that the number of colors Q is at least delta to the 1 over K roughly. And in the case of deterministic algorithm, Guo, Liu, Lu, and Zhang shows that there is an approximate counting and sampling algorithm if Q is at least delta to the 14 over K. And in the case of randomized algorithm, this constant 14 is then improved to 9 in the work of Vuong, He, and Yin. And in our other work last year, we improved this constant from 9 to 3 essentially. And in subsequent work by He, Sun, and Wu, the same result is also obtained. And in fact, they don't only obtain approximate sampling algorithm, but they can also exactly sample from a uniform distribution on the satisfying assignments. Okay, in fact, Galanis, Guo, and Wang also proved that it is NP-hard to approximately count if Q is smaller than delta to the 2 over K. So these two bounds are now only off by this factor of 3 and 2. Okay, so far we have discussed specific applications of the Lovász local lemma. But let's recall that the Lovász local lemma applies in very generally to constraint satisfaction problem with no assumption on the structure of the constraint satisfaction problem. So can we achieve a sampling version of the Lovász local lemma where we can count or sample under a condition that is like the LLL condition with no further assumptions? In this direction, we have the work of Vuong, He, and Yin, where in the case of atomic constraint satisfaction problems, so those are constraint satisfaction problems such that each constraint can only be violated by at most one assignment of its variable. They show that there is a sampling and counting algorithm if P times delta to the 350 is smaller than a small constant. And to translate this to the general setting of general constraint satisfaction problem, essentially we would have this condition here where we replace the delta by n delta, where n is the maximum number of assignments violated in one constraint. And then in this setting, our other work last year improved the constant 350 to roughly 7.043. And in fact, our constant is not fully optimized. And then in later work by He, Sun, and Wu, this constant is replaced by 5.714. But let me remark that in many applications of the Lovász local lemma, the atomic setting or this constraint or these constraints here are in fact quite restrictive. So let's consider, for example, the case where all variables are Boolean and each constraint depends on exactly k variables. In particular, P will be at least 2 to the minus k. So this would not give anything non-trivial if n is larger than 2 to the k over some large absolute constant. On the other hand, in many uses of the Lovász local lemma, the probabilities of the bad events are controlled using concentration inequalities, such as Chernoff bound. And in those cases, typically n is much larger, perhaps closer to 2 to the k over 2 or even 2 to the k minus epsilon k. And note that in those cases, the Lovász local lemma still guarantees a satisfying assignment, even allowing for delta that grows exponentially in k. So our main result that I want to discuss today goes in this direction, that provides a general algorithm for approximate counting and sampling that works for general constraint satisfaction problem in a condition that, that looks like the LL condition. So if we have a general constraint satisfaction problem, and let's assume that each variable is contained, it takes value from an alphabet of size at most q, which is bounded, and each constraint depends on at most k variables, which is also considered here an absolute constant. Then essentially, as long as p times delta to the 7 is small, there is a deterministic algorithm to approximately count, and also an efficient algorithm to approximately sample the satisfying assignment. So here, compared to the Lovász local lemma condition, we are only off by this factor of 7. The runtime of our algorithm is like Moitra's deterministic algorithm of the form n to the poly delta k and log q. So it's only polynomial if delta and k and q are considered as constants. But this is typical for deterministic approximate counting algorithms. And in particular, this implies that for KC-NF formula, we have a deterministic approximate counting algorithm up to delta smaller than roughly 2 to the k over 7. And for Q colorings, we have an approximate counting algorithm for Q at least delta to the 7 over k. So even compared to previous works, even in the setting of randomized algorithm, these improve over the best previously known thresholds. So in the next part of the talk, I will try to give a very quick overview of the main proof ideas. And for simplicity, I will only discuss a randomized algorithm which works when p times delta to the 10 is smaller than a constant. So in order to go from the 10 to the 7 in the theorem, we will need a further careful averaging martingale argument. And finally, let me remark that while I will discuss a randomized algorithm, the algorithm we consider can be de-randomized very easily using the standard method of conditional expectation. Okay, so what is our high-level approach to the counting algorithm? It will essentially consist of 2 steps. In the first step, we will find a sequence of good guiding partial assignments we call P0 up to PS, which satisfy these 3 nice properties. First, we want that for each constraint, the conditional probability that the constraint is violated, given the partial assignment, is at most some parameter p prime that we will choose later. And we want PS to be extendable to a full satisfying assignment. And finally, we want the constraints which are not yet satisfied in PS to break into small connected components, which have logarithmic in n size. So let's call SPJ the set of satisfying assignments that extend the partial assignment PJ. Our goal is then to approximate SP0, which is the total number of satisfying assignments. And we write SP0 in terms of this telescoping product. And in particular now, to estimate SP0, it is sufficient to evaluate SPS and the ratios SPL over SPL plus 1. Now we use the third property of the guiding partial assignment. We will have that we can actually evaluate SPS exactly by exhaustive enumeration in polynomial time, because the formula at that point breaks into connected components that have logarithmic size. So it only remains to evaluate these ratios. And towards this goal, we will use a generalization of a very nice method of Moitra that tries to evaluate these ratios by setting up a linear program. So let's next discuss the first step in the algorithm, which is to find a good guiding partial assignment. And for this step, we will use a randomized greedy algorithm. And these insights here are actually date back to Beck's work on algorithmic local lemma and are quite often used in the early works on algorithmic versions of the local lemma. So how does this algorithm work? We will order the variables arbitrarily, and then we will go through the variables one by one. Each time we encounter a new variable, we will assign to it a uniformly random value from its alphabet Q. After that, we will move the variable from the available set to the set of assigned variables. But after assigning each variable a value, we will go over the constraints and check if there is any constraint where the conditional probability of violation becomes too large. If it exceeds the threshold P prime, then we will declare the constraint frozen. And if the constraint is frozen, then we will also freeze all of the remaining variables that are not yet assigned any value in the constraints as frozen. And we will put those into the frozen set F. And the frozen variables will never be assigned any values in subsequent runs of the algorithm. So they will stay unassigned until the end of this randomized greedy algorithm. And we will repeat this until there are no available variables. In particular, a variable is either assigned a value in the partial assignment or it is frozen. So why does this work? Well, first, from the definition of the algorithm, we can see that the conditional probability of violation of each constraint is bounded roughly up to a constant by P prime. And this is because whenever a constraint has conditional probability of violation exceeding P prime, we immediately freeze that constraint and no variable in that constraint is further set to any value. And then if we assume that P prime times delta is small, then by the existential version of the local lemma, the partial assignment can be extended to a full satisfying assignment. This is the second required property for a good partial assignment. And the most important property is that the final proper partial assignment that we obtain, the unsatisfied constraint in this final partial assignment will break into small connected components with high probability. And in order to prove this, we use a structure called 2-3-3 that dates back to the work of Alon in 1991. Okay, so this will complete the first step in our algorithm. And in order to complete the approximate counting algorithm, we need to be able to approximately evaluate the ratios SPL over SPL plus 1. So how do we do this? Let's call VL the vertex that is assigned a value when we go from the partial assignment PL to the assignment PL plus 1. And for each character A, let's call PL of A the partial assignment that extends PL by assigning VL the value A. It is easy to see that in order to estimate this ratio, it is sufficient to approximate all of these ratios SPL of A over SPL of B, where A and B range over the alphabet. Essentially, what we are doing here is to try to approximate the marginal of the vertex VL in the distribution of satisfying assignments conditional on the partial assignment PL. And in order to motivate our algorithm, let me first describe an idealized coupling procedure. So in this coupling procedure, we will always keep track of two partial assignments. And we will start with the partial assignments PL of A and PL of B that differ only at the vertex VL. So in each step of the algorithm, we'll keep track of a set of dangerous variables, a set of assigned variables, which are assigned values and the remaining variables. So we will choose a variable from a constraint that is not frozen, which contains both a dangerous variable and a remaining variable. After that, we will try to assign the values to this variable in both partial assignments using the maximal coupling of the marginal distribution of this vertex of this variable conditioned on the two partial assignments. And then as in the randomized greedy algorithm, we will freeze any constraint whose conditional violation probability becomes too large. And we will declare also all of the disagreements between the two partial assignments as the dangerous variables. So the main step in the analysis is to prove that the coupling procedure actually terminates at logarithmic depth with high probability. This is again using 2-3-3. And also we can prove that for the leaves XY of the coupling procedure. So at the two partial assignments of the coupling procedure where it terminates at a logarithmic depth, we can compute exactly the ratio Fx over xy in polynomial time by exhaustive enumeration. And given these two input, we can now set up the clever linear program of Moitra and obtain our approximation of SPL of A over SPL of B. So in order to go from 10 to 7, essentially what one needs to do is to combine both steps, finding the partial assignment and estimating the marginal into one analysis that has to be done carefully. Okay, so this is our paper. Thank you.